Yeah, so 10 minutes to cross the bay, and I've got to talk to 5 people along the way. It's always the same people, so I know them pretty well now. Don't know what they look like, but I talk to them every day. So that's maybe a great example of how we need all the UAM research that's going on at NASA right now. So PK invited me here to talk, and he didn't tell me what he wanted me to talk about, so I got to choose how I spend the next half hour of your life, which is kind of fun. And the thing I want to talk about, you might notice if you look at the little informal logo I put on my hat here for Heaviside. Informal, don't worry, no trademark violation. I'm a bit of a NASA fan, and so I just wanted to talk about some of the ways in which fundamental research out of NASA, you might not think of how it applied to these things, but just some cases where it's been really useful to us. We move very fast on these programs. We don't have time to go do a lot of fundamental research ourselves, and it's the sort of thing that lets us go quickly. And I should have a little, here we go, a little clicker. So first I'll show you a little bit about what we're doing to set the stage. So this is Heaviside. This is a little single-seat electric VTOL aircraft. It's a bit of a mouthful, but think of just an aircraft where you can go land it wherever you want to land it. And we test these out near Hollister right now. Our goal, instead of building an electric helicopter replacement, we want to go for what we see as a better long-term solution, something that gets you where you're going. I do this commute now. I fly Oakland. I land in Palo Alto. I have a little foldy bike. I'm 10 minutes in the air, but I've got 40 minutes of all sorts of other stuff that I'm doing to get to work. So you really need to go small. You need to go exactly where you're going for it to really be worthwhile. And if you want to have a lot of these out there in the world, we don't think this is a short path, but that's where we want to go in the long run. If you want to have a lot of these aircraft out there in the world, you've got to be quiet. They've got to be fast, which is actually nice because then there's less of them in the airspace. You got to be able to go pretty far, and most importantly, I'd say it has to be efficient. So about a quarter of greenhouse gas emissions right now are transportation. This is probably the part I'm most interested in electric aviation. And why not, if you're trying to build a new industry, why not go for something that's just better than what's out there today? So this aircraft here, we're about a third to a half of the energy per mile of a Tesla, while going many times as fast. So I think that's pretty good. But that efficiency is a little hard to get. It's a challenge. So to do that, I'm just going to talk about one element. You can't do it without getting the maximum performance out of every part of the aircraft. So I'm going to talk about one element, pretty distinctive element, which is this forward-swept wing that we have. The forward-swept wing is there so that we can put the propellers in the same place as the wing, while also having them behind the wing. Let me see if I can explain that a little better. I put this little CFD picture in the corner. We put the rotors behind the wing so that when we're taking off and landing, we can suck air over the wing. It's like a duct. We get this really nice beneficial effect between the two parts of the aircraft, between the lift system and the aerostructure. So we get this really nice benefit. We have to sweep the wing forward, though, so that the center of lift of the wing and the center of lift of the propellers are at the same place. It's really important. And to do so, there's pretty much this is kind of the only way you can do it. You have to put this fairly significant amount of sweep in the wing. This is a pretty non-traditional way to do aircraft. And so when we're looking at concepts to figure out what we're going to do, we saw that as a risk. You go look at other high-efficiency aircraft, and they tend to look like this. And this is where a lot of our aerodynamics are inspired from. I'm a sailplane pilot. A lot of folks on the team are sailplane pilots. This is what we know. And aircraft like this, you make them super efficient with long laminar runs. Here's, I don't know how many people here build aircraft? I don't know how technical the audience is. Raise your hand if you build aircraft. All right, now we'll leave it non-technical. So when when a wing hits the air, you're basically building up this glove of air around the wing that's insulating it from the rest of the airstream and lowering drag. So if we look on the right side of the picture, then that's where the air is hitting the wing. And this is an oil flow test. We've got a bunch of oil on there, and we can kind of see how much the air is dragging on the surface with it. And you see after a while, maybe halfway through the picture, we get to these little spots. And that means the glove of air has gotten so thick that it's not really impacting the wing that much. Then this thing happens, that straight line in the middle, that's transitioned to turbulent flow. You go to turbulent flow, everything gets much thinner. That air is grabbing the wing again, slowing you down. And so it's super important you try to get this long laminar flow as the air goes over the wing to keep it as efficient as possible. And if you go back to this, you'll see this is really easy to do on an aircraft like this. There's tons of flight heritage. There's tons of design heritage. You can just go pick something out of a book and use it. A little more challenging when you start putting significant sweep on an aircraft to get that. So this is probably the aircraft you'd look at, kind of iconic NASA test vehicle. We'd say, well, you're building forest-swept wings. This is what you might look at to learn from. But it's not the one that was most important for us. And so instead, I want to talk about this F-14 test, which is pretty important for us to make our decision on this aircraft. And I think it's a great example because you probably wouldn't think that this would be the kind of thing that would feed into electric aircraft. So this is a case where NASA took a glove, they glued it onto an F-14 wing, and it's a really great flying test bed. You can go out there, you can sweep the wings forward, you can sweep them back, and you can see what happens at different angles. And I don't know if there was a particular goal in mind, maybe transport aircraft. I'm sure something very different than what we're doing. But NASA went out, did the work. The information's available for free. And I was very happy when I found this. I got this chart here. It's not super important to dig into the details. I'm not going to bore you with 6 little plots, but the main thing is if you look over here, I have a little pointer. Let's see, you look over here, you see different wing sweep angles. You see different spots where it transitions to that turbulent flow that is not as efficient. And you can choose a wing sweep angle that you can get away with so that we get both the really efficient wing and we get the position of the propellers for this really efficient takeoff. And then we were able to go to the tunnel and validate this. So here's actually a picture of tunnel testing of the same thing. We can see there we go. We can see, see what the real problem is that happens. The air kind of flows down the front of the wing before it goes across the surface. Sorry, in this case, it's going the other direction. It's going from that side, right to left. I can't do directions. I'm dyslexic. And we get, based off of that paper still, we get this nice long laminar run that we were able to validate and put on an aircraft. And this is really important for us. We can go out there, we can test in the real world. This thing flies 100 miles already with reserves. Longest range electric VTOL aircraft in the world that I'm aware of. I'm pretty sure it's the longest range anyone's actually achieved. It can fly really fast. It's another nice side effect. So it's actually a lot faster than the gas plane I fly to work right now, in addition to being maybe 20 to 30 decibels quieter, 100 to a few hundred times quieter. So that was a huge part of making this work. And in the time frame we developed this, we went about 6 months from concept to a first flight of a prototype. It's rather fast. There's not exactly a lot of time in there where you can go do testing and go feed that testing back in. So this sort of fundamental research being out there is super important for us. Here's another great example. This is maybe just for fun. I don't know how many people are already aware of this. This is Colonel Stapp back in the 50s when people were a little more intense in what they'd allow to do in fundamental research. He strapped himself to a rocket sled many times, actually, and would do deceleration tests in this case, it was for the development of ejection seats. Now, we have a tiny aircraft. We can't really fit an ejection seat in there. Actually, the whole aircraft weighs the same as an ejection seat, so it's not really going to work. But really important fundamental research that gives us charts like this. And I find this chart so impressive because all these points, for each point up here, Okay, for most of the points up here, I'll be exact. For most of the points up here, there are human tests. And these were people like Colonel Stapp who put themselves on rocket sleds and went and tested to the limit of human exposure so that we have charts like this today, and we can go do crash sizing, and we can build crash-worthy structures, which is incredibly important. If you want to go build safe aircraft, you have to do safety in layers. You can't say you're not going to crash. You have to say what happens when it happens, in addition to all the things you do in flight to make it safe. So that is very useful. And then I want to share one more tie-in on this program, where you take those same rocket sleds, and this is actually a test failure. This was a test failure from JPL. This is testing parachute, I believe, for Mars deceleration. And there was a design problem on the parachute, overloaded it, and they split it. You wouldn't think this would be very useful for us, but it actually is. When we are developing our own ballistic parachute systems for our own safety systems, you know, I say the thing weighs about the same as an ejection seat. It actually has its own ballistic parachute, so the whole aircraft can come down kind of like an ejection seat. We can go look at tests like this, and we can see how they fail, and we can use that to inform how we plan the failure of our own parachutes if something goes wrong, the sequence of what can happen if you break one. So this is actually incredibly useful for that. I'll talk a little bit about another program that I ran for a while. This company still exists. This is part of Google now. I sold it to Google. This is Makani Power. And this is a bit of a strange concept. So first, maybe I'll give a sense of what we're doing here. And I'll say this is something that's very hard to take to market, but it's a wonderful design challenge to learn how to build large electric aircraft. And what we're actually doing is we are, time delay, there we go. We are flying a tethered aircraft, and we are pulling against the wind. So we're slowing air down as it goes by. We're harvesting that energy, the same as a wind turbine blade does, but without the structure. And we actually built one of these, called it the M600. We're not very imaginative in our naming then. And built one that's about the size of a 737 in wingspan, so a very large aircraft. And we took it out, and it's actually flown off of a moored offshore platform in Norway. So very hard design problem. And one of the things I'll point out, just another interesting aerodynamic problem, it has this huge tether stuck to it. That is really hard to drag through the air. So you have this huge problem to drag this big, ugly tether through the air as you're flying this thing, while still keeping it efficient and harvesting a lot of power. The best way to do this is an extremely high lift airfoil. And the way that we are using this is nothing like the high lift system on a commercial aircraft or on the little, pedal jumper that I fly, or on Heaviside. Very different design regime. It wants to be high lift all the time. It's almost more like an F1 car in terms of that. So we had to figure out what to put on the aircraft. We had to come up with a new class of airfoil. And one of the most useful things for this is actually the rendering here. This is Fun3D, which is a NASA code that we used at Makani and use at Heaviside now for all of our aerodynamic simulations. And this is validation that was done and shared. Data from this was shared. It was a high lift system test. So it is testing, kind of a commercial transport design. I always hit the wrong, there we go. And it's a little more traditional, the design. We've got the little slats and a long straight wing you can tuck all the high lift systems into and cruise, and a big flap on the back. But still, the availability of that fundamental research let us go calibrate our models and design a system that was pretty good at operating at high lift coefficients. So this thing, typical aircraft, my little DA-40, I fly, and you might stall at a CL of 1.4. This thing stalls at twice that, which is pretty good. So this is just to give a picture of the operations. This is a really weird system, very hard to describe. It's probably one of the first vertical takeoff and landing electric aircraft. We just didn't know that we should be in the aircraft market at the time. So it takes off from a floating platform. That tether it's reeling out is actually a solid piece of carbon fiber. This is a challenge. If you pull that piece of carbon fiber to failure, you can actually shoot little shards of carbon fiber through bulletproof glass. There's so much energy released. Don't worry, that doesn't happen in the, out in the real world. You reel that out under hover, and then you start flying it in circles and pulling it against the ground station. That slows air down, you harvest energy, you make power, you send it back down the tether. So that's another case. We have this totally different class of airfoils, not really like anything out there that we can model it on today. And we had to figure out what we were going to do to build this vehicle, and we relied heavily on Fun3D and on this NASA high lift system design. So this is, I think at the time we didn't know it was supposed to be hard. So that's maybe the only way we made it work. It's about 10 times harder than making electric aircraft, and it's a much harder market. So it's really cool to see it still go. That's still at Google, or sorry to say at Alphabet. Came out of Google, sold into Google X, got spun out of Google X. It's part of Alphabet now, in partnership with Shell. And but it was a great spot for us to learn the fundamentals of building electric aircraft. So that, just a few examples. They're all over the place. Anytime doing new concept design or looking at what we can get away with in terms of building efficient aerostructures, kind of the first spot we stop is the NASA archives. So thank you.
Did we do the conference I/O for this? I mean, and if not, that's fine. We have people here that can easily raise their hand and ask some questions. So let me first turn to the audience. Yeah, please, Pete.
So are you planning to develop this vehicle at the same size, or is this a prototype for a larger version of it that you want to build?
I love how everyone asks that. It's a good question. I think the standard approach is you go try to build an electric helicopter replacement, and then you can fly a bunch of rich people around, and that's kind of already done. It's pretty boring, actually. So we're trying to step over that. We're trying to go past that stage. I think that's it's a more interesting problem, and scaling up to spend an extra $1 billion on development to then scale back down seems like a waste of money to me. Yeah, so that's a great question. I love this as an example. The X-29, there was a lot of research on forward-swept wing stability. And fighter jets, you build very thin wings so that you can get good transonic and supersonic performance because, turn rate at the corner speed is essentially the thing that determines whether or not you win or lose in kind of a energy limited fight. So super important for fighter jet design. In our case, I mean, this thing's fast for a GA aircraft. It's faster than what I fly to work, but it's no fighter jet. And so we looked at that and we thought we might have to do something. We actually found it was a pretty simple problem structurally. And you just go through the analysis and find we could do a very traditional aerostructure. It's really nice.
Other questions? Great. Actually, I'm sorry. Hold on just a moment. Do we have a microphone back there that we could pass around to make sure? Oh, we do.
Toss it?
That's what it's for. Yeah. Make sure we can all hear.
So I was impressed by the optimization you did for the wing to get performance. Have you looked at eliminating the tail by using differential and vector thrust to bring weight down?
Yeah, yeah, it's, you know, my controls lead. We've we go back and forth about this a lot. You know, it's nice just to have something that you go out and you fly and you know how it's going to behave. You can't spin this thing. We try to spin it. We try to get in a situation where it'll depart. It's really hard. And then when you go remove a tail, now you have to worry about what if you hit a strong gust? You know, what if you get outside of the regime in which you have the control authority to control the thing? So it's just a more complex problem. It may go that way in the long run, but you know, the thing I like is really fast, really efficient aircraft that I can fly today. That's my thing. So that's why we left the tail on for now, and I think, you know, in the long run, that's the kind of optimization we might look at.
Other questions? Please.
Okay, I can project.
There may be some people online, so we want to make sure they can hear you too.
Yeah.
It's coming right behind you.
You got it. Does that work? I guess it does. And new style instead of old style out of drama class. Okay, so you got 100 miles. What storage technology are you using? Is that just lithium batteries?
Just, I don't know, batteries. I don't know if they're good or bad.
Thank you.
They're ones I can get today. That's what I like. My whole optimization is stuff I can get today. Yeah. Yeah, when you're, the other thing I'll add is when you're trying to get out there in 6 months, you can't go do a lot of fancy stuff. You have to really pick and choose. So we're not really, under the hood, it's a pretty simple airplane.
Jerry.
Hey,
Yeah. I'll do maybe one more here.
try to do it old-fashioned. I just want to say, you know, I took a lot of aero classes in college and always loved your designs. I didn't know they were coming out of the same team. I bring up that wind power example 2 or 3 times a year to show people, like there are still people doing good work, and they can design planes with clean lines that, you know, that actually get the whole process. So
Thank you.
just my compliments. It actually convinced myself and some other people that your video you released recently was CGI.
That drone, so we filmed that with a drone, and that drone had to land like 5 times while we were filming to change batteries.
Yeah.
We had this really fancy film crew out, and you know they would ask, "Okay, we're going to bring it down to change the batteries. Do you want to land for a second?" It's like, no, we'll just keep going. It's good.
Just beautiful footage, and that's how I finally convinced myself it was real, is the motion of the aircraft is correct, and you almost never see that in CGI. You know, you can see the weight of the vehicle and how it's loading up and turning.
Yeah.
So anyway, my compliments. It's
Well, thank
great
you.
design work, and it's unfortunate it's so rare these days.
I think there's a lot of great design work going on out there. Honestly, there are some neat new things. I also am excited that NASA's doing X-planes again. We're kind of getting past that phase of like not doing exciting things. So, no, I think there's a lot of great design work going on. But thank you.
We're pretty excited about that ourselves. So, actually, one question from me, if you could.
All right.
You did show some wind tunnel testing that you're doing as part of this overall development. Where did you get that done?
I wish I could say I did it here.
No, that's okay.
Your wind tunnels are hard to book.
Indeed they are.
They're kind of filled up. Actually, a friend of mine built a wind tunnel in a hangar, and we actually built our own as well not for like clean flow testing, but for endurance. Just in a building around here. So we did that down at Specialized Bicycle. They've got their own tunnel. So real practical, really nice way to just get out there, but nowhere near the quality of any of the Ames tunnels. And all the tunnel infrastructure that was built in the 30s through the 50s is pretty incredible.
But again, as you're pointing out, given your objectives, it's not necessarily what you need in order to get flying and to begin to evaluate and to explore.
Yeah, the booking time was 6 months, so we wrote it off.
You've been pulling through.
Yeah, would have doubled our time.
Yeah, great. All right, Damon, thank you very much.